Hello students. So in the previous class we started with eigenvalues and eigenfunctions associated with a second order linear differential equation. In that context we also introduced something called Sturm-Liouville problem, and today's lecture will be dedicated to the similar topic, that is basically finding out eigenvalues and eigenfunctions of Sturm-Liouville equations. So if you recall, our Sturm-Liouville equation had this particular form. So we had something of this type, Sturm-Liouville equation. So it was of this type. So we had ddx of px into dy dx plus qx y plus lambda rx y equals to 0. So from here we can write it as px y double dash plus p dash x y dash, and this one will be qx plus lambda r x into y. So this is basically our general form of Sturm-Liouville equation, and of course we can complement it with some initial condition, boundary conditions, and things like that. Now I can show you some examples where basically we can have a given equation. So for example, suppose we are given px and qx and rx, and we need to find out the correct form of Sturm-Liouville equation. So you might be given px, qx and rx and will be asked to write the correct form of it, right? So if we want to do that, suppose we have this equation. So example would be convert the equation minus of y double dash plus x to the power 4 y dash equals to lambda y to Sturm-Liouville problem, right? And so we are asked to do this. So from here we can, what we can do, we will take our capital P is equals to 1, capital Px equals to 1, and capital Qx or small qx, whatever, small qx equals to minus of x to the power 4, and then in that case we will determine something called integrating factor. So integrating factor would be so as we are trying to put it into that d of something, so that means we are basically looking for an integrating factor. So I will write mu is equals to e to the power minus of e to the power qx dx. So this will be e to the power minus of x to the power 4 dx. So this will become e to the power minus of x to the power 5 by 5. So if I multiply this equation by e to the power minus of x to the power 5 by 5, then this will become minus of e to the power minus of x to the power 5 by 5 y double dash plus e to the power minus of x to the power 5 by 5 x to the power 4 y dash equals to lambda y e to the power minus of x to the power 5 by 5, right? So this can be written as ddx of I have y dash. So this is basically our this term, no? P dash x. So P dash x can be named as capital Qx for the time being. So this is basically y dash, and I have e to the power minus of x to the power 5 by 5 equals to lambda e to the power minus of x to the power 5 by 5 into y. So now we can see this is basically our there is a negative sign here, so we will have a negative sign. So this is the required Sturm-Liouville form, because this is ddx of e to the power minus of x to the power 5 by 5 y dash, small q is basically 0, and then we have lambda rx is e to the power minus of x to the power 5 by 5. So this is the required Sturm-Liouville equation. What you can do at best, you can bring this on the right hand side, and therefore this will reduce to this plus this equals to 0. So this is also the required Sturm-Liouville equation form. this matches exactly with this one, right? So it may be given that find out the Sturm-Liouville form of the given second order differential equation. So basically you have to identify that how I can write ddx of that first and second term in a way. So what kind of integrating factor do you need? So here if you picture this as if you take dy dx equals to, let's say right hand side is 0, and if you put dy dx equals to v, then this will become dv dx minus of dv dx plus x to the power 4 v equals to 0. Suppose for the time being right hand side is 0. So from here I can determine the integrating factor as e to the power minus x to the power 4 dx, right. So that's the integrating factor I multiplied with, and this gives us the required Sturm-Liouville equation form, right. Since it is mostly related to finding out the eigenvalues and eigenfunctions, we have done some examples related to that. Let me just quickly summarize. Depending upon what kind of boundary condition, what kind of equation do we expect, what kind of eigenvalues and eigenfunction do we expect to get. So just to summarize, suppose if we are given Dirichlet boundary condition, boundary condition, so I am calling it as Dirichlet problem. If we have given Neumann boundary condition, I will call it Neumann problem, and if Robin boundary condition, then we will call it Robin problem. So Dirichlet boundary condition or Dirichlet problem is something of this type, y double dash plus lambda square y equals to 0, and this equation is valid on 0 to L, and I have at x equals to 0 I have 0, and at x equals to L I also have 0. It does not have to be 0, it can be any number, but taking 0 simplifies things. So from here our eigenvalues lambda n will be n pi by L. If L is 1, then it will be simply n pi, right, and n is running from 1, 2, 3 dot dot and so on, and x and x the y and x, the eigenfunction will be sine n pi by L of x. Yesterday we had L equals to 1, or in the previous class we had L equals to 1, so that's why it was n pi by n pi x simply. Okay, next we have Neumann problem or Neumann boundary condition. So if we have Neumann problem or Neumann boundary condition, then we have y double dash plus lambda square y equals to 0 for 0 less than or equal to x less than or equal to L, and I have y dash at 0 equals to y dash at 0 equals to 0, and y dash at L is also equals to 0. Also we can have non-zero boundary conditions, but we can take 0 as well. So in this case the eigenvalues will be lambda n pi by L, and n running from 1 2 3 0 1 2 3 0 1 2 3 dot dot and so on, and our eigenfunction will be cos n pi by L into x. Alright, now third could be the periodic boundary condition. This also we talked about, the periodic problem or the periodic boundary value problem. So here in this case we will have y double dash plus lambda square y equals to 0, and we will have y at minus L and y at plus L, they are both equals to 0, and y dash at minus L and y dash at plus L also equals to 0. So this is like a periodicity condition. So whatever you have at minus L, same condition we have at L, and whatever we had at y dash at minus L, same condition we have y dash at plus L. So from here we will get lambda n equals to n pi by L, where n is 0, 1, 2, 3 dot dot and so on, and our eigenfunction y and x will be 1 cos of n pi by Lx and a sine of n pi by Lx. So it can be combination of these three functions. It can be any of these functions if we have periodic boundary condition. Fourth one is if we have mixed boundary condition, mixed problem. If we have mixed problem, let's say of type 1, mixed problem type 1 or type A. So then in that case we have y double dash plus lambda square y equals to 0. I have y at 0 equals to 0 and y dash at L equals to 0. So from here I will get lambda n equals to 2n plus 1 by 2L into pi, where n is running from 0, 1, 2, 3 dot dot and so on, and our eigenfunction y and x will be sine of 2n plus 1 by 2L into pi into x, right. So this is our mixed problem of type A. Then we have mixed problem of type B, mixed problem type B. So type B is just like type A with small modification. The small modification is x dash at 0 is 0 and x at L is also 0. So from here the eigenfunction will be lambda n 2n plus 1 by 2L into pi, where n is running from 0, 1, 2, 3 dot dot and so on, and y and x is cos of 2n plus 1 by 2L into pi into x. So this is the required eigenfunction. So depending upon what kind of boundary condition is given, whether you have Dirichlet, whether you have Neumann, whether you have Robin boundary condition, whether you have mixed boundary condition, type A, type B, will end up getting that kind of eigenvalues and that kind of eigenfunction, right. All of these problems are somewhat falls under the category of Sturm-Liouville equation, right. So here we stated 5 different types of second order ordinary differential equation associated with different boundary conditions. That's why, I mean, the equations were same, but the boundary conditions were different. Consequently, we have different types of eigenvalues and eigenfunctions. If we need to solve, then we have already solved 1 or 2 examples before. First of all, let me summarize few properties of the Sturm-Liouville equation, and then we will maybe do one more example. So the properties of Sturm-Liouville problem. So first of all, the properties of eigenvalues. So the first property is the eigenvalues of SL equation are all real. Okay. Then the second property is there are an infinite number of eigenvalues with lambda 1 less than lambda 2 less than dot dot up to lambda j, which tends to infinity as j tends to infinity and C is lambda j is positive provided the coefficient functions Px and Qx are positive, right. And second one is eigenfunction related to eigenfunctions. A number property is for each, so I can write for each lambda j there exists or there is an eigenfunction phi j that is unique up to a multiplication constant, that means phi j and c into phi j, right. So, it is unique up to a multiplicative constant and which satisfies okay, now a property will start, which satisfies a phi j x are all real and can be normalized so that integral 0 to t or 0 to L Rx phi j square x dx will be 1, and second one is the eigenfunction eigenfunctions corresponding to different eigenvalues, eigenfunctions corresponding to different eigenvalues are orthogonal, with respect to weight function Rx. That means integral from 0 to L Rx into phi j phi k, of course they are functions of x, dx equals to 0 where j not equals to k, and C number property is phi j x has exactly j minus 1 zeros on 0 comma L. That means phi j x has j minus 1 zeros or roots on 0 comma L, and these are the three properties related to eigenfunctions. So, we have eigenvalues and then we have eigenfunctions. For lambda j's, that is the previous result, coefficient function qx is positive, and if lambda 1 is equals to, let us say we have lambda 1 is alpha 1 plus I beta 1. So, first of all the eigenvalues are all of Sturm-Liouville equations are all real. There are an infinite number of eigenvalues such that they all tend to infinity as j tends to infinity, and lambda j is positive provided the coefficient function qx is positive, and I think there must be one more condition. So, we have let me just quickly check. So, we have yes, we have boundary conditions associated with Sturm-Liouville equation. So, qx is positive, and if I have px into, I am going to quickly write y dash of y dash minus of plus of qx plus rx into lambda into y, right, and then we have some boundary conditions, that is alpha y0 plus alpha 2 y dash 0 equals to 0, and beta 1 yl plus beta 2 y dash l, right. So, this is our Sturm-Liouville equation. So, of course, qx needs to be positive, and another condition is alpha 1 by alpha 2. If I am naming them alpha 1 alpha 2 and beta 1 beta 2. So, here we have lambda j's, they will be all positive if the coefficient function qx is positive, and this is the coefficient, basically qx I am calling it as coefficient function. So, qx is positive, and then I have alpha 1 by alpha 2 less than 0 and beta 1 by beta 2 greater than 0. So, I think there is no role of px, right. We have a qx, so qx needs to be positive, and then alpha 1 by alpha 2 here and beta 1 by beta 2 here. So, this needs to be negative and this ratio needs to be positive, right. So, now if that happens, then all the eigenvalues will be positive, but it does not, I mean, when we calculate the eigenvalues, it does not always have to be that they will all be positive. First of all, they will all be real, that is for sure. Then there are an infinite number of eigenvalues with lambda 1 less than lambda 2 up to lambda j, and they all tend to infinity as j tends to infinity. I mean, eventually as j tends to infinity, lambda j will tend to infinity. And important thing is the eigenvalues will be positive for all j. I mean, it should be positive if the coefficient function, that is qx, that is positive, and alpha 1 by alpha 2 is less than 0 and beta 1 by beta 2 is greater than 0. So, if this happens, then we can say that lambda j's are positive, and for the eigenfunctions, for each lambda j there is an eigenfunction phi j that is unique up to a multiplicative constant. That means either you have phi j or you have c times phi j, right. So, it is unique only by multiplying with a constant, but you still have the same phi j, and which satisfies, let me go to this. So, which satisfies following conditions. So, phi j or following property, phi j's are all real and can be normalized. So, normalized in the sense you multiply by a function r can also be 1. So, this will become mod of phi j over L2 norm, right, in 0 comma L whole square equals to 1. So, this is like norm, so normalized, and that is always 1. So, that is what we mean by normalization. And the eigenfunctions corresponding to different eigenvalues are orthogonal with respect to a weight function Rx. This Rx can also be 1, or it can be some other function such that phi j into phi k multiplied by that function, that will become 0. So, then you say that phi j and phi k are orthogonal, and phi j has exactly j minus 1 zeros on 0 comma L. So, if all these things happen, then we say that phi j, the eigenfunction, has these properties. All right. We can try to solve or summarize few more properties. Another property, that is, so we have for eigenvalue, eigenfunction, and then third property is expansion property. Expansion property. So, suppose phi j x, so phi j x are complete if fx is if f is piecewise smooth. Phi j's are complete if fx is piecewise smooth, then fx can be written as summation n running from 1 to infinity Cn into phi n x, where Cn's are given by integral from 0 to 1 or 0 to L, since we have L everywhere, Rx fx into phi n x dx divided by integral from 0 to L Rx into phi n whole square x d of x, right. So, this is the first property associated with the expansion property. So, then observation, few observation, the Sturm-Liouville operator and the boundary conditions are such that the Sturm-Liouville operator, that means L, and the boundary condition, the operator L and the boundary condition are such that we have integral from 0 to L v into L u dx equals to integral from 0 to L u into L v dx, and this implies that L is a self-adjoint operator, operator. The way we understand self-adjoint matrix here is just that it is translated to operator. So, self-adjoint operator, and So all these things, whatever properties that I have written, they can be proven. It's just that because of time constraint we are not proving it, but you can find the proof in any textbook where they are dealing with eigenvalues and eigenfunctions and Sturm-Liouville equations, right. Now we have mentioned several properties associated with it. Maybe we can solve one example, and then that will close this chapter. So one example that we can consider is Robin boundary condition or Robin problem. So suppose our given equation is x double dash plus lambda capital X, lambda square for better understanding, and lambda or lambda we can take, and lambda equals to mu square, and x dash at 0 equals to h1 into x at 0, and x dash at L equals to minus of h2 x at L. We can write in short x dash at 0 minus of h1 x at 0 equals to 0, and x dash at L plus h2 x at L equals to 0. So this is our Robin problem. So obviously here we take that h1 or hi simply greater or equal to 0, just for sake of the calculation. So from here the solution can be written as directly x equals to a cos mu x plus b sin mu x, very straightforward way, and we can calculate x dash x because our boundary condition involves dashes. So we have mu and minus of a sin mu x plus b cos mu x. Now we will use all these boundary conditions, and if we use the boundary conditions, then from first one we can, from boundary condition 1 we will be able to obtain a is equals to capital B mu by h1, and from boundary condition 2 we will be able to obtain x dash L. So we have x dash L equals to minus of a mu sin mu L plus b mu cos of mu L, which is equals to minus of h2 x at L, and this is equals to minus of h2 a cos mu L plus b sin mu L. So from here if we simplify we will get b minus of mu square by h1 plus h2 sin of mu L plus mu h2 by h1 mu cos of mu L bracket close. So therefore from here we will get tan of mu L equals to mu h1 plus h2 divided by mu square minus of h1 h2. Now case will arise, we will have to consider three different cases. So first case will be when h1 and h2. So from here we can have three possibilities. So first one is when h1 and h2 they are both non-zero. So of course they are greater or equal to 0, but they are both non-zero. So then what will happen, I mean we will see that our mu n which will be n pi by L, and this as n running from 0, 1, 2, 3 and so on, and our eigenfunction xnx will become mu n by h1 cos of mu nx plus mu n by plus sine of mu nx, right. Now similarly we have to consider the case when h1 is 0 and h2 is non-zero. So when h1 is 0 and h2 is non-zero, then we will obtain similarly our mu n from here, and we can calculate our xn, and when h1 is non-zero and h2 is 0, so then what will happen, so that also we can determine. So either they are both non-zero, h1 and h2, then h1 is 0, h2 is non-zero, then h1 is non-zero and h2 is 0. So here in this case we can also find out what will be our eigenvalues and what will be our eigenfunctions, right. So this particular example which deals with Robin boundary condition, up to calculating the general solution is same. Now how you use the boundary condition to determine the eigenvalues and eigenfunction plays an important role, and these all fall under our Sturm-Liouville equation category. So here x double dash can be written as d dx of 1 dot x dash in a way, and no, there is no x dash, no? So here, but basically this can also be visualized as a Sturm-Liouville problem, because I mean this is very simple case, because we can write ddx of 1 dot y dash, and then your px is basically 1. So this is again falling under our Sturm-Liouville problem category, and once we have the Sturm-Liouville problem, we can do this general solution. From there we can use the boundary conditions to eliminate any constants which are eventually equal to 0, and then by doing by using the second boundary condition, you may try to obtain eigenvalues in terms of n, pi and l and all that, and then we can write down the eigenfunction, right. So more or less all the problems in this chapter will be of the similar type. You have to find out the eigenvalues and eigenfunctions, and from there we can solve these equations. All right. So I will stop here today, and this chapter ends here, and now we have very last topic left, which is Laplace transform and the solution of ordinary differential equation using Laplace transform. So we will start them in our next class. So thank you for your attention, and I will see you in the next class.